Chapter 15. Structure of atoms and nuclei. Exercises pages 3. Exercises. Choose the correct option. In which of the following systems will the radius of the first orbit of the electron be smallest? 1. Hydrogen 2. Singly ionized helium 3. Deuteron 4. Tritium. Solution. Tritium. Exercises Q1.2, page 342. Choose the correct option. The radius of the fourth orbit of the electron will be smaller than its eighth orbit by a factor of 1. 2, 2, 4, 3, 8, 4, 16. Solution. 4. Exercises Q1.3, page 342. Choose the correct option. In the spectrum of the hydrogen atom, which transition will yield the longest wavelength? 1. N equals 2 to N equals 1 2. N equals 5 to N equals 4 3. N equals 7 to N equals 6 4. N equals 8 to N equals 7. Solution. N equals 8 to N equals 7. Exercises Q1.4, page 342. Choose the correct option. Which of the following properties of a nucleus does not depend on its mass number? 1. Radius 2. Mass 3. Volume 4. Density. Solution. Density. Exercises Q1.5, page 342. Choose the correct option. If the number of nuclei in a radioactive sample at a given time is n, what will be the number at the end of two half-lives? 1. N2 2. N4 3. 3 N4 4. N8. Solution. N4. Exercises Q2.1, page 342. Answer in brief. State the postulates of Bohr's atomic model. Solution. The postulates of Bohr's atomic model, for the hydrogen atom. 1. The electron revolves with a constant speed in a circular orbit around the nucleus. The necessary centripetal force is the Coulomb force of attraction of the positive nuclear charge on the negatively charged electron. 2. The electron can revolve without radiating energy only in certain orbits, called allowed or stable orbits, in which the angular momentum of the electron is equal to an integral multiple of h2 pi, where h is Planck's constant. 3. Energy is radiated by the electron only when it jumps from one of its orbits to another orbit having lower energy. The energy of the quantum of electromagnetic radiation, i.e., the photon, emitted is equal to the energy difference of the two states. Exercises Q2.2, page 342. Answer in brief. State the difficulties faced by Rutherford's atomic model. Solution. 1. According to Rutherford, the electrons revolve in circular orbits around the atomic nucleus. The circular motion is an accelerated motion. According to the classical electromagnetic theory, an accelerated charge continuously radiates energy. Therefore, an electron during its orbital motion should go on radiating energy. Due to the loss of energy, the radius of its orbit should go on decreasing. Therefore, the electron should move along a spiral path and finally fall into the nucleus in a very short time, of the order of 10 to 16 s in the case of a hydrogen atom. Thus, the atom should be unstable. We exist because atoms are stable. 2. If the electron moves along such a spiral path, the radius of its orbit would continuously decrease. As a result, the speed and frequency of revolution of the electron would go on increasing. The electron, therefore, would emit radiation of continuously changing frequency, and hence give rise to a continuous spectrum. However, the atomic spectrum is a line spectrum. Exercises Q2.3, page 342. Answer in brief. What are alpha, beta and gamma decays? Solution. Exercises Q2.4, page 342. Define excitation energy. Solution. The excitation energy of an electron in an atom. The energy required to transfer an electron from the ground state to an excited state, a state of higher energy, is called the excitation energy of the electron in that state. Exercises Q2.5, page 342. Define ionization energy of an electron in an atom. Solution. The ionization energy of an electron in an atom is defined as the minimum energy required to remove the least strongly bound electron from a neutral atom such that its total energy is zero. Exercises Q3, page 342. State the postulates of Bohr's atomic model and derive the expression for the energy of an electron in the atom. Solution. The postulates of Bohr's atomic model, for the hydrogen atom. 1. The electron revolves with a constant speed in a circular orbit around the nucleus. The necessary centripetal force is the Coulomb force of attraction of the positive nuclear charge on the negatively charged electron. 2. The electron can revolve without radiating energy only in certain orbits, called allowed or stable orbits, in which the angular momentum of the electron is equal to an integral multiple of h27t, where h is Planck's constant. 3. Energy is radiated by the electron only when it jumps from one of its orbits to another orbit having lower energy. The energy of the quantum of electromagnetic radiation, i.e., the photon, emitted is equal to the energy difference of the two states. Consider the electron revolving in the nth orbit around the nucleus of an atom with the atomic number Z. Let m and e be the mass and the charge of the electron, r the radius of the orbit and v the linear speed of the electron. According to Bohr's first postulate, centripetal force on the electron equals electrostatic force of attraction exerted on the electron by the nucleus. I.e., the energy of the electron in a stationary energy state is discrete and is inversely proportional to the square of the principal quantum number. Exercises Q4, page 342. Starting from the formula for the energy of an electron in the nth orbit of the hydrogen atom, derive the formula for the wavelengths of Lyman and Balmer series spectral lines and determine the shortest wavelengths of lines in both these series. Solution. According to Bohr's third postulate for the model of the hydrogen atom, an atom radiates energy only when an electron jumps from a higher energy state to a lower energy state, and the energy of the quantum of electromagnetic radiation emitted in this process is equal to the energy difference between the two states of the electron. This emission of radiation gives rise to a spectral line. The energy of the electron in a hydrogen atom, when it is in an orbit with the principal quantum number n, is. Exercises Q5, page 342. Determine the maximum angular speed of an electron moving in a stable orbit around the nucleus of the hydrogen atom. Solution. Exercises Q6, page 342. Determine the series limit of Balmer, Paschen, and Fund series, given the limit for Lyman series is 912A. Solution. Exercises Q7, page 342. Describe alpha, beta and gamma decays and write down the formulae for the energies generated in each of these decays. Solution. Exercises Q8, page 342. Explain what are nuclear fission and fusion, giving an example of each. Write down the formulae for energy generated in each of these processes. Solution. Nuclear fission is a nuclear reaction in which a heavy nucleus of an atom, such as that of uranium, splits into two or more fragments of comparable size, either spontaneously or as a result of bombardment of a neutron on the nucleus, induced fission. It is followed by the emission of 2 or 3 neutrons. The mass of the original nucleus is more than the sum of the masses of the fragments. This mass difference is released as energy, which can be enormous as in the fission of 235 U. Nuclear fission was discovered by Lise Meitner, Otto Frisch, Otto Hahn and Fritz Strassmann in 1938. The products of the fission of 235 U by thermal neutrons are not unique. A variety of fission fragments are produced with mass number ranging from about 72 to about 138, subject to the conservation of mass energy, momentum, number of protons Z, and number of neutrons N. A few typical fission equations are: a type of nuclear reaction in which lighter Otto C nuclei, of low atomic number, fuse to form a heavier nucleus, of higher atomic number, with the release of enormous amount of energy is called nuclear fusion. Very high temperatures, of about 107 K to 108 K, are required to carry out nuclear fusion. Hence, such a reaction is also called a thermonuclear reaction. Example: the DT reaction, being used in experimental fusion reactors, fuses a deuteron and triton nuclei at temperatures of about 108 K. Exercises Q9.1, page 342. Describe the principles of a nuclear reactor. Solution: in a nuclear reactor, fuel rods are used to provide a suitable fissionable material such as control rods are used to start or stop the reactor. Moderators are used to slowing down the fast neutrons ejected in nuclear fission to the appropriate lower speeds. The material used as a coolant removes the energy released in the nuclear reaction by converting it into thermal energy for the production of electricity. Exercises Q9.2, page 342. What is the difference between a nuclear reactor and a nuclear bomb? Solution 1. Nuclear reactor. A nuclear reactor is a machine where electricity and heat energy is generated by utilizing the power of atoms. In this mechanism, nuclear chain reactions are produced, controlled, and contained, releasing a tremendous amount of energy. This controlled energy is used in electricity generation and radioactive isotopes production. These isotopes are used in the treatment and research of cancer in the medical field. All operating nuclear reactors are critical. When reactors are running at a constant power level, they are said to be in a critical condition. These reactors use heavy atoms as fuel instead of fossil fuels. Fast-moving electrons strike a radioactive nucleus such as plutonium-239 or uranium-235, causing the nucleus to split. This splitting process is known as fission. In the process of fission, a tremendous amount of energy, radiation, and free electrons are released. These free electrons that are released are guided to strike other nuclei and so on, causing a chain reaction. Neutron moderators and neutron poisons control these fast-moving electrons and slow them down while becoming absorbed in other nuclei, thus managing the output of electricity from a reactor. The moderators are heavy water, and solid graphite. Nuclear bomb. In a nuclear bomb, there is a nuclear device having massive destructive power coming from uncontrolled fusion and fission reactions. The fusion and fission processes generate a tremendous amount of energy with a small amount of matter. This matter is usually the unstable nuclei of plutonium-239 and uranium-235. An atom bomb is categorized as a fission bomb and a hydrogen bomb as a fusion bomb, or both weapons of mass destruction. In World War II, Hiroshima and Nagasaki are recent examples of such mass destruction. In fusion bombs, nuclear fusion is the result of a huge amount of released energy, while in the case of fission bombs the released energy is the result of fission reactions. Solution 2. In a nuclear reactor, a nuclear fission chain reaction is used in a controlled manner, while in a nuclear bomb, the nuclear fission chain reaction is not controlled, releasing tremendous energy in a very short time interval. Exercises Q10, page 342. Calculate the binding energy of an alpha particle given its mass to be 4.00151 U. Solution. Data. M equals 4.00151 U. MP equals 1.00728 U. Mn equals 1.00866 U. 1 U equals 931.5 MeV C2. The binding energy of an alpha particle equals ZMP plus NMN, MC2. Equals 2MP plus 2 million, MC2. Equals 2, 1.00728 U plus 2, 1.00866 U, 4.00151 U, C2. Equals 2.01456 plus 2.01732, 4.00151, 931.5 MeV. Equals 28.289655 MeV. Equals 28.289655 times 106 electron volts times 1.602 times 10 to 10 J. equals 4.532002731 times 10 to 12 J. Exercises Q11, page 342. An electron in hydrogen atom stays in its second orbit for 10⁻8 s. How many revolutions will it make around the nucleus at that time? Solution. Data. Z equals 1, m equals 9.1 x 10 to 31 kg, e equals 1.6 x 10 to 19 c, epsilon 0 equals 8.85 x 10 to 12 c2 nm2, h equals 6.63 x 10 to 34 js, n equals 2, t equals 10 to 8 s. Exercises Q12, page 342. Determine the binding energy per nucleon of the amenctum isotope to be 244.06428 U. Solution. Data. Z equals 95, n equals 244 to 95 equals 149, MP equals 1.00728 U, Mn equals 1.00866 U, M equals 244.06428 U, 1 U equals 931.5 MeV C2. The binding energy per nucleon. Exercises Q13, page 342. Calculate the energy released in the nuclear reaction. Atom and of helium atom to be 7.016 U and 4.0026 U respectively. Solution. 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 Exercises Q16, page 343. Sample of carbon obtained from any living organism has a decay rate of 15.3 decays per gram per minute. A sample of carbon obtained from very old charcoal shows a disintegration rate of 12.3 disintegrations per gram per minute. Determine the age of the old sample given the decay constant of carbon to be 3.839 times 10⁻12 per second. Solution. Data. 15.3 decays per gram per minute, living organism, 12.3 disintegrations per gram per minute, very old charcoal. Hence, we have exercises Q17, page 343. The half-life of is 28 years. Determine the disintegration rate of its 5 mg sample. Solution. Exercises Q18, page 343. What is the amount of necessary to provide a radioactive source of strength 10.0 MCI, its half-life being 5.3 years? Solution. Data. Activity equals 10.0 MCI equals 10.0 x 10 to 3 C equals 10.0 x 10 to 3, 3.7 x 10 dis S equals 3.7 x 108 dis S. T1 half equals 5.3 years equals 5.3, 3.156 times 107 S equals 1.673 times 108 S. Exercises Q19, page 343. Disintegration rate of a sample is 10 per hour at 20 hours from the start. It reduces to 6.3 by 109 per hour after 30 hours. Calculate its half-life and the initial number of radioactive atoms in the sample. Solution. Solution. Data. T1 half equals 272 D equals 272 times 24 times 60 times 60s equals 2.35 times 107 S. A0 equals 2.0 micro C equals 2.0 times 10 to 6 times 3.7 times 10 equals 7.4 times 104 dis S. Solution. Exercises Q22, page 343. Before the year 1900, the activity per unit mass of atmospheric carbon due to the presence of 14C averaged about 0.255 becquerel per gram of carbon. A. What fraction of carbon atoms were 14C? B. An archaeological specimen containing 500 milligrams of carbon shows 174 decays in 1 hour. What is the age of the specimen, assuming that its activity per unit mass of carbon when the specimen died was equal to the average value of the air? The half-life of 14C is 5,730 years. Solution. Exercises Q23, page 343. How much mass of 235 U is required to undergo fission each day to provide 3000 megawatts of thermal power? Average energy per fission is 202.79 MeV. Solution. Data. Power equals 3000 megawatts equals 3x109 J/s. Therefore energy to be produced each day equals 3x109 x 86,400 J each day equals 2.592 x 1014 J each day. Energy per fission equals 202.79 MeV equals 202.79 x 106 by 1.6 x 10 to 19 J equals 3.245 x 10 to 11 J. Therefore number of fissions each day. Exercises Q24, page 343. In a periodic table the average atomic mass of magnesium is given as 24.312 U. The average value is based on their relative natural abundance on Earth. The three isotopes and their masses are 23.98504 U, 24.98584 U, and 25.98259 U. The natural abundance of is 78.99% by mass. Calculate the abundances of other two isotopes. Solution.